This slide shows that how we compute the velocity of a p point on a rotating rigid body. So right now, if you want to get a velocity of p, and if we want to describe as a vector, the velocity is, this is vector, cross product, and r. So this is position vector actually. That is this r vector, and this is your final velocity. And then this omega is pointing out from this screen. Okay, so this is perpendicular to the plane. And if you think about acceleration though, acceleration has two different components. The one component is this tangential components, and the other one is normal components that's always directed to the center. And tangential components can be expressed by alpha cross product r vector, and then normal component is omega square r vector. And this omega square r vector can be write down omega square and r. Then let's say if this is the unit vector of normal direction, then you can say omega square r un. But since your r vector can be written like r and un, that's why we just simply write omega square r. We want to do the relative motion analysis. Relative motion analysis is a tool to help us to get the velocity and acceleration of points on a rigid body based on a relative velocity and a relative acceleration. And let's start with the example. In this simple example, just imagine that you have a rod, okay, and this is just ground, smooth ground. And if you just let it go, this kind of rod start kind of moving this way and moving this way, and finally it just fall like that. Okay, so it's kind of slip and then going this way. So if you just think about this one, this is actually undergo general plane motion. So if you think about this rod motion, the rod is undergo translations and plus also rotation as well. Let's say this is starting position 1. It just kind of slide down and move this way. So let's say this is 2. So since this undergo general plane motions, we can think about these motions as if this rod translate from 1 to 2 position, plus after it translated, then everything is rotating about A. This is very this is obvious, because if you translate the rigid body from here to here, after that about A, if you rotate it, your final position is the same as the second position, right? And here point A is called base point in this analysis, and usually the point A is chosen because we know some information about point A, such as velocity of A, acceleration A is known. Then we want to consider that to be our base point. Then if you just look at this one, so when you translate this rod kind of rigid body from left to right, then the velocity of B here has the same as velocity of A, right? And after that you just rotated it, right? So rotate it with a certain angular velocity omega, then your velocity here is omega r. So that's why if you combine, if you add this velocity and this velocity, which is here, this is VA, and this is the velocity due to the rotation. If you just add that, that will be your absolute velocity of point B at this here. So that means at this instance, the absolute velocity V is here, because your absolute velocity B is the additions of the velocity of the B under the assumptions that everything just undergo translation motions, plus the velocity under the assumptions that everything is rotated about the base point A. That is your actual velocity of B. So, as I wrote down here, okay, your velocity B can be found by adding the velocity of base point here, because we want to add right now, just ignore any rotation or motion, then any point of the rigid body have the same velocity. That's why the VB should be equal to VA. Okay, but after you translate it, you have to rotate about A, so we want to add this velocity as well. Okay, so this is the angular velocity of the rod, and this is the position vector B from A, because everything is rotating about A, so the A should be your kind of reference. Then you have to think about the position vector pointing the B from A. Okay, so using this kind of concept, you can get the velocity of any point of your rigid body is equal to the velocity of a base point plus the angular velocity of that rigid body cross product the position vector of that point from your base point. Just look at the example. So right now the roller A moving to the right 3 meters per second, and the velocity of B, I want to find the velocity of B. Okay, I want to find the velocity of B at the instance theta is 30 degrees. Right now this rod is moving like that, and then we know that this is 30 degrees, and this is A, and this is B. Okay, so I want to find what's the velocity of B, and then I know the informations that at this instance A has a certain velocity 3 meters per second. Then what's the length of this one? 1.5. So the length of the rod is 1.5 meter. Okay, then I want to find the velocity of B, so my V can be found by VA and plus, then I do not know what's the angular velocity of the rod, and then I have to find out what's the position vector B with respect to A. Okay, then everything is, this is my X and this is Y, so RBA vector can be found like minus 1.5 cosine 30 I and plus 1.5 sine 30 J. Okay, that's my R, and then my VA is 3 I. Okay, meter per second, this is meter. So let's try to find the VB. So our VB is equal to 3I, and omega is, I do not know what is omega, so I just want to use omega k, and cross product minus 1.5 cosine 30 I plus 1.5 sine 30 J. Then this is 3I, and if you do the cross product between k and I, that should be J, right? So omega minus 1.5, this is times cosine 30, and Ki and J, and plus k and j. So kj cross product result in I, negative I. So this one should be negative 1.5 sine 30 I. That. So we have 2i. So let's combine the I. So this one is like sine 30 I. Okay. And then minus 1.5 omega cosine 30 j. And this is left side is BB. But right now, if you look at that, there's constraint because the roller is always touch the wall B, right? So which means the velocity of B is always just going down. So I know that my velocity V has only J component only. I don't have any I component because this is just going down. So in these equations, you equate the J to J, but right now on the left side there's no I, right? Which means this component is 0. So from this equation, from these conditions, you can compute what should be the omega. Once you get the omega, you plug that a number into here. That will be the velocity of B. Okay, so this is the simple kind of example, or I explained how we get the velocity using relative motion analysis. So why we call this is relative? Because this is relative the vector, because this is position vector of B of interest from your base point. This is relative. So because we use any term relevant to the relative positions, so we call this is relative motion analysis for velocity. Okay, then how about the acceleration? Look at that. Acceleration it has the same concept. So we interpret our motion as if we translate first, okay? Translate first, and then plus rotate, okay, about a base point A. Then whenever this is translate, any point, the velocity of any point has the same as A here. So that's why your VB has same velocity of AA. That's why your VB is equal to AA. After that, you rotate it, okay? As long as you rotate about A, this one has like a circular motion. That's why it has tangential components. Tangential components can be written alpha cross product the position toward the position pointing B from A, and also normal direction AN, which is omega square the position vector. So this is the equations to get your velocity acceleration of point B using the relative motion analysis and with the option of knowing the acceleration of A. So we have include the acceleration velocity with this one. So at this time, let's try to find the angular acceleration of the rod, okay, alpha, and acceleration of B at this instance. Right now, our AB kind of switched. A previous example, we call the bottom as A and up as B, but right now it just switched. Okay, right now, since we know the velocity of A, velocity of A, and velocity of acceleration of A, let's say I want to make this is my base point, okay? And this is kind of moving this way. So I want to kind of interpret the motion is like basically the later times later, this one just kind of moving in this way, okay, just sliding down. So I want to kind of think about this motion like first I want to, this is my starting position, but I want to translate everything, which means I just translate everything from top to down, and plus this is my A point, this is B, and A and B. And then about the A, I just rotate. So I first do the translation plus rotate. Okay. So I can write down my equation like a VB is equal to my VA and plus omega and R like that, and this should be B from A. And my acceleration B is my AA plus alpha and R A and omega square and R B A like that. So I want to use these two equations. So right now my VB, right now the B has always contact with the ground. So my VB has only I direction only, okay? So that means I have only J direction. My VA is down, so that's 6J. And then I don't know omega yet, so I omega K. And cross product of my R pointing B from A. Okay, so here, this is 4 and 5, right? This is 4 and 5. So probably we can get the certain distance from here to here. So the 5 square is equal to 4 square and that d square. So 25 and 16 and d square. So if you just combine this one, you know that d should be 3. Okay. That means your R vector from A to B should be 3I and negative 4J. Why negative? Because this vector from A to B, so this is your vector. So this one has positive and this one has negative, right? So this is my VB. So from here I can 6J and Ki, Kj. So Ki is J, so 3 omega J, and Kj is negative I, so 4 omega I. So right now I know that Jj, so this should be 0. So from here I know that my omega should be 2. Okay. And then once I figured out my VB should be is equal to 4 omega, so that's why this is 5 meter per second. Okay, so that means this one should be 8 meter per second. How about the acceleration? Acceleration AB, okay, AB. So right now acceleration has only x direction as well. So I want to write ABI and plus 0J, okay, and AA have negative 5J, okay, and alpha I do not know alpha, so I alpha K and 3I 4J, and we got the omega 4 and 3I 4J. So if you just compute that, this is 5J, and Ki is J, and Kj is negative I, and 12I, and 16J. So if equate the left side to the right side, ij separately. So this is j, this is j, and this is j. Everything should be 0. That means minus 5 plus 3 alpha plus 16 should be 0. So from here you can get the alpha. Okay. Once you get the alpha, you plug into these equations to get AB. And here I want to introduce another analysis, another method to analyze the velocity using a concept of instantaneous center of zero velocity. So what is instantaneous center of zero velocity? For any object undergoing planar motion, okay, so right now this one undergo general plane motion, it just rotate and also it translate. Then there always exists a point in the plane of the motion at which velocity is instantaneously zero. What's that mean? What does that mean? So at this instance, okay, it seems like everything. Even though this one goes even though this one undergo translation and rotation motion, you can find certain points, not necessarily inside the rigid body, even outside. Then you can consider this motion as if this motion has a pure rotational motion about that point. What does it mean? So if you look at this one, so right now this is exactly same motion, it has the same velocity like that. But if you imagine, if you try to find a certain point here, and then let's say you kind of attach one like a bar like that, so this is fixed on here, then this motion is same. That means you can just generate exactly same motion rotating this rigid body with this kind of bar about the C. That means if you rotate all this rigid body about the C with this omega, then this left side motion and right side motion becomes identical. So it's kind of very interesting concept. Then this C is called instantaneous center of zero velocity because it doesn't have any translation motion. It has only pure rotation about the C. So at this instance, the velocity C should be 0. So once you find any point that has instantaneous zero velocity, we can analyze your motion as if your rigid body is rotated about that point. Let me show you more example here. So we have a kind of wrong rod, and if this one is slide down, then this rod undergo general plane motion because this is rotating and also at the same time translating. Then if you just imagine that you have a certain point outside of the rigid body, and this is kind of one rigid body, then this rod motion here and this one exactly same. If you rotate this one rigid body about this point here, C, in a case it seems like we just rotate this whole rigid body about the C. Then if you're just thinking about only the edge of the rod, it has exactly same motion of this one. Okay, so that's why we call this instantaneous zero velocity point. And then at this instance, the velocity should be 0. How about the bottom part? So this is just the wheel. Okay, wheel is rotating without slipping. Then because your ground doesn't move, so every point of your ground has a zero velocity, and at this point, the C, it has a contact point. So this contact point should has the same velocity with the velocity of your ground, which means this is a 0. Then we can consider this C is instantaneous zero velocity points. That means you can think about this wheel motion as if you rotate your wheel about this point with a certain angular velocity. This is possible, and then this velocity, angular velocity, is the same as this wheel angular velocity. And then since you rotate about the AC, if you try to think about the velocity of center, so this one looks like circular motion like that. That's why your V is equal to R omega. Okay. How about the point here? So if you want to find the velocity here, it looks like everything is rotating about like that because you rotating about C. So this one should be, the velocity should be 2R and omega. Look at that. If this one is kind of sliding down, okay, sliding down, you know that the velocity of B is always pointing down and velocity A is pointing this way. But you can certainly think that you can find one IC point, then everything is moving, rotating about IC right now. So since this is rotating about IC, if you try to find the velocity of B, so this is 90 degree, so this one should be, let's say this is D, so velocity is d omega. And how about this one? Let's say this is 90 degree and the length from here to is d2, then your velocity VA is d2 omega. So then how about the velocity of here center? So as long as you can find the distance and that perpendicular distance from this rod, then your velocity is just this one because everything is rotating about IC. So as long as you know this distance from center to that point of your interest, then your velocity is d3 and omega. Okay. The benefit of having the IC point is, like, if you know the velocity of any point of your rigid body, you can just get the distance from IC to that point. Then however, you need to find so if you once you find the distance from IC to any point of your interest, then you can just multiply your omega, then that will give you just the velocity. So what if I want to find the velocity of point here? Then you can try to find the distance, okay, from here to here. Then you just multiply omega, then that should be your velocity of that point. Okay. How about here? Then you can just find the distance, and then this should be your velocity. So your velocity is always perpendicular to that line you found that represent the distance from IC to the point of your interest. How about this wheel? I told you that in the wheel without slipping, the contact point is always your IC. Okay. Then if I want to know the velocity of any point here, then as long as you just know the distance from your point of interest to IC, then you can just multiply omega. Then that should be your velocity. So this is omega and this distance d. Okay. If you want to know the velocity of here, you just compute the distance from to here that and multiply omega. Then you will get this velocity and so on.